I talked about a couple of different things. The last couple of times, we've learned that the change in internal energy is the heat that flows at constant volume. So if you have a constant volume process and you measure the heat through calorimetry, you will have measured the delta U. Now I'm mixing up my D's and my deltas, which you should never do. I take off points for that, but luckily I didn't take off points on my own notes. The change would be QV, okay? So that's what happens at constant volume. At constant pressure, a couple of days ago, I think, we related the change in enthalpy. We defined enthalpy and found that it is the change in, that it is the heat that flows at constant pressure, excuse me. And if you integrate, you get this. So the thing is now, these are two big thermodynamic parameters, and we really would like to know, how are these related? And I just barely started to talk about that last time. And I started with the first law. First law, du is dq plus dw. So this is the first law in differential form. If there, and then normally what we do is we put in the different kinds of work, because we really have to say, if we want to just have this be the work, we have to say there is no extra work. Extra work is really important, but we haven't gotten to it yet. We'll get to it later. So if there's no extra work, then we have du is dq plus the work of expansion. Okay, and then I'm also going to do this. I'm going to say at constant pressure. So if the pressure is constant, then dq becomes dqp. It becomes the heat that flows at constant pressure, which is also the change in enthalpy, dH, because we just figured that out up here. So we have this sort of formula, that the change in internal energy is the change in enthalpy plus the work. Okay, so what this tells us, because we could, if we looked at the integrated form of this, well, we don't have to. We can just think about it in terms of differentials. That these two are not equal if there's expansion work. Okay, so there are many cases where they are equal. Okay, so if for example, if you have a reaction and it happens like in solution, I believe I gave this to you last time, this is sort of where I ended, and no gas is generated, that happens a lot. So there's really no volume change. No expansion work is done. And then du would equal dH, or delta U would equal delta H. But if not, so if work is done either on the gas or done by the gas, then delta U will be delta H plus the work, which will be expansion work. We've already said no extra work. We're not considering that yet. Okay, so, all right. So when you think about it, delta U equals delta H under these situations, if no work is done, the vast majority of the energy changes that are associated with reactions come from making and breaking covalent or ionic bonds, and in some cases, disturbing intermolecular forces or things like that. So I would say that mostly it's the making and the breaking of bonds that is responsible for the bulk of the delta H and the delta U. Okay, and those things are the same. That reaction is going to have the same bonds broken and the same bonds made, and they're both contributing in the same way to the delta H and the delta U. So this is why in Gen Chem, you know, there are some Gen Chem books that spend pages talking about the relationship between delta U and delta H, and I just try to gloss over the whole thing and say, you know, let's talk about constant pressure, and then we can just call one the same as the other. And I don't bother too much with this whole thing about whether work was done or not. But in PChem, we need to deal with the work because we need to have an accounting of all the changes, and we need to obey the first law. So the reason why these are equal when there's no expansion or compression is because that mostly it's the making and the breaking of bonds that matters. And so, yeah. Then there are, you know, some other things that affect that affect delta U and delta H, which we're going to handle. We're going to derive equations for that. So we actually do need to consider cases where work is done and these two things differ. So what happens when work is done? And delta H and delta U differ. Okay, so that's where we're at today. Okay, so I would like to talk about the common cases where these two thermodynamic changes are not the same. Okay, and there are three that I would call common cases. So the first one I've kind of mentioned because I talked about changing. Well, maybe I didn't, but it doesn't matter. So the first one is reactions that change the number of moles of gas. So a lot of times this is a gas phase reaction, or it could be a reaction where a gas is produced. It doesn't have to be all gases. But what happens is that this, if gas is generated, right, this leads to an expansion if gas is generated, or clearly a compression if gas goes away. There are reactions where gases can turn into things in solution. Okay, now a lot of times this only leads to kind of a small correction. That's especially true in combustion reactions. There are some changes in moles, and it really doesn't lead to a very big change in delta U or delta H. They're very similar. We're going to do an example of that today. So often this ends up being a small change, a small difference. But if you have a reaction where you're generating a ton of gas, like when TNT explodes, I'm sure there's a much bigger difference there because you generate many moles of gas. But sometimes it's, you know, sometimes it's greater influence. Okay. Then the second thing is processes where a gas is generated from a liquid or solid. And this would be most common if you have a vaporization or you have a sublimation. Okay, so for example, if you vaporize a liquid or you have a solid that sublimes, like iodine. Okay. So clearly there is a big expansion going on there. You start with something that has a very small volume relative to the volume of the gas. And so here you have a large expansion. And this causes there to be a bigger difference between delta U and delta H. Okay. And third, we have a situation when you're heating a gas Because as you know, as you heat a gas, increase the temperature, that gas expands, okay? At least if you're doing it at constant pressure, so not at constant volume. This causes a lot of expansion, and so work is done. And you can have a rather large difference between, in fact, for both of these, you can have significant differences. Okay, so so I'd like to start by sort of deriving the common expressions that we use to solve problems like this, and then we're going to work on two different problems. I don't know how far we'll get, but I hope that we get, you know, pretty far along. So let's derive some of these, deriving the common expressions used to relate delta U and delta H. Okay. And they all come from the same thing. Well, first of all, we start with the definition of enthalpy, U plus PV. So this is just a definition. And then we often do this. We take the differential of both sides, so we consider changes. Okay. And remember, when we do these things with differentials, it's like they need to use the rules of derivatives. But what I want to do here is not break this down into PDV and VDP, because I want to first consider what happens. You know, I want to talk about what happens at constant pressure. So if pressure is constant and you're taking the derivative of pressure times volume, then pressure would just come in front of that derivative. So that's what I mean by saying we use the same sort of rules that you use when you take derivatives. So this dH would be du plus P dV, okay? And it's as if we had plus VDP, but we canceled the dP because the pressure is constant. So now if we just sort of integrate these things, and the P is on the outside, right, because it's constant, we would get that delta H is delta U plus P delta V. And indeed, this is the first of our derived expressions. This is actually the one we use, I think, when you vaporize a liquid, like, because you just get a change in volume in going from the liquid to the gas. But I'll get into that later. Okay, so but what I want to do next, before I get into the other expressions, is I want to go back to the dH is du plus PdV. Remember, this came from the definition of enthalpy, but I want to look at this a little bit closer. I want to look at the PdV term here, because it's going to tell us something that we already knew. Okay, so if you look at this, if you just flip it, yeah, if you flip it around and you solve for du, and you think about what is this thing here, okay? And remember, the only kind of work we have is expansion work, and you could see that this is actually dW expansion. So really, all this is guess what? The first law. Because at constant pressure, which I've said already, right? This dH is dQP. Right, so we took that definition of enthalpy. We merely said constant pressure. The dH we already know is dQ at constant pressure. It's the heat that flows at constant pressure. And the constant pressure allows us to take that out of the derivative. And so it looks an awful lot like the work of expansion minus PdV. So we basically have the first law. So I think what I'm going to do as we do these derivations is I'm going to show you where the first law comes in. because you could recast each one of these little derivations, mini derivations, as being another way of writing the first law for this particular situation. Okay. All right, so let's go back to where we were. So we were over here. We were here. I'm going to copy that down. DH. Take that down here. Is DU plus PDV. Okay. Actually, it was DPV. Let's start with a more general one. And the reason I went back a step, right, I really went back to this step here, is because most of the time in these types of problems, we're dealing with generation of a gas or expansion of a gas, and we can treat those gases as if they were ideal. So PV is nRT. So basically what causes these expansions in these problems is gases. So can use the ideal gas law. All right. So this becomes du plus d nRT. And now what we do is we break this down. We break this down into two different cases. The case where the temperature changes, but the gas moles are not changing. So that would be for a heating, for example, where you're not changing the number of moles of the things you're heating. So we're going to break this down into if the temperature changes, but the moles of gas stays constant. So that's one of the things we're going to have. And the other one is if the moles changes, so the moles of gas changes, but the temperature stays constant. Okay, and like I said, this one here on the left is used for if you're heating a gas. Okay, and this one on the right would be used like for a reaction. Sorry about that, don't know what happened there. Yeah, hold on a minute. So this is used for, I'm not muted, am I? No. Used for a reaction that generates a gas, or where the moles of gas changes. Okay. And so for both of these, we start in the same place. dH is du plus d nRT. And now, okay, what if T changes, but moles is a constant? Well, then moles is constant, R is of course constant, and we get to take these in front of the derivative. So we end up with nR dt. Okay, and so now this can be integrated. Well, the integral of dt is just delta t. It's t from t1 to t2. We have nr delta t. This is delta u and delta h. So we have a nice equation for relating delta h and delta u in cases where the temperature is changing. Okay. And then you can see where I'm going with this, I hope. That we have dH is du plus d nRT. And now we have a case where the moles is changing, but the temperature is constant. So the temperature can come out as well as R, of course. So this becomes RT dN. And again, we can integrate this because temperature is a constant there. It's easy to do. Delta H is delta U plus RT delta N. And we also had, remember, I pointed this equation out to you. Okay. And now I want you to go back and remember I said I was going to relate all of these to the first law. And if you remember, we had at constant pressure, we had delta U is delta H, which now remember that was QP, plus WEXP. Hold on, did I get that wrong? Yeah. Okay, so delta H would be delta U minus the work of expansion. Wait a minute, hold on. No, sorry, I don't want to do that. This is just the way I wanted it right here. I guess I better put it the other way. Delta U is QP plus W expansion, right? We have no extra work. So this is the first law. And that's delta H because the pressure is constant. QP is equal to delta H plus the work of expansion. Okay. Yeah. So all right. So now, remember, so this came from the first law. And notice that's exactly the way each of these is written. It's got the delta H equals delta U plus this other term, just like down here, which came from the first law. So that means that each of these circled terms are the negative of the expansion work. Okay, so just, so, you can always tell yourself, remind yourself that delta H and delta U would be the same if it wasn't for expansion work. So here, yeah. Or you could think about it this way, delta U is delta H minus NR delta T. This is Q, and this is W. That might be the easier way to think about it. This is Q, this would be W. Okay, and this one as well. This would be Q, and this would be W. So you could think about this all in terms of the work and the heat. All right. So let's do a problem. Let's do an example. That's what we're about. I want to do an example. So here is an example. I gave this out last time, but I never got to it. Well, I didn't give it out. I sent it. Okay, so I don't want to necessarily do this problem for you. I wouldn't mind you reading it, thinking about it, trying to do it for 5 or 10 minutes, and then maybe you'd be a little more interested in seeing how it's solved. So, but I want to tell you that what you're going to do is you're going to use this equation here. This delta U is minus C delta T. It's similar to that the change in internal energy would be NCV delta T, except that these things are combined together to make the calorimeter constant. And there's a negative sign. I think I've explained before that that's because the temperature changes now have to be measured in the surroundings. So if you use this equation and you're given the C here and you're given the change in temperature, you can calculate the delta U. All right, now, so what your job is to first of all find delta U for this process. And then it says, what is delta U per mole? All right, so really we could use this little 0 here to represent that. That is a standard change in internal energy. That little 0 there means that we're talking about 1 mole. It means we're talking about standard pressure of 1 atmosphere and standard temperature. Okay. 298. So you can call this a delta U 0, and then it asks you to find the delta H per mole. And now what you have to do is think about what's going on here. It's the combustion of ethane. Okay, so you know what the formula for ethane is, right? And you know it's a gas, and you have to combine it with oxygen, and you know what the products of combustion are. So what you have to do is you have to write this equation, because remember what you're figuring out now. Once you've got, you multiply that minus C delta T, that gives you the change in internal energy. And you could divide by the number of moles and get the molar change in internal energy. But then you have to figure out what delta H is for this process. And that entails writing the chemical equation here, figuring out what is the change in moles. Okay, so what I'd like to do is to have you really work on this. I'm going to just put you in 2 groups and work on it just for like 10 minutes. Okay, see how far you can get, because you'll come up with some questions and I want to be able to answer them rather than just talking to you about it. So that's what I think I'm going to do. So let's see, just put in just 2 rooms. Oh, God, I hate teaching this way. All right, that was really fun, talking when no one could hear me. Maybe we'll just do this problem together. Now I don't even know what's going on. Oh, they'll close in 32 seconds. Wow, that's great. How about closing them right now? All right, I don't know how well that worked, but maybe you got to look at this problem a little bit before we do it. So just about everybody, I just want to make it easier. Let's make it 6.460. So we will keep the 4 significant figures. All right, so we have the delta U. We'll use the formula minus C delta T. I can do this because the heat that transfers at constant volume, right? This is a constant volume calorimeter. The heat that transfers at constant volume is the delta U. This is minus 10.42 times 6.46. I'm putting a 0 there because I want 4 sig figs. The reason being is that there's really not a big difference between delta U and delta H. And that's 67.31 negative. That's kilojoules. Okay, that's the delta U. Now it asks you for the delta U per mole, which we often write this way. Okay, has a few other things that have to be true for that little 0, but we're assuming they're true. So we have to figure out the number of moles. So you already, I know some people already figured out that this is 0.04350 moles. So you would take the kilojoules and divide it by moles. And that comes out to, yes, as Dina said, 154. She probably couldn't hear me saying, yes, that's the same answer. And I keep an extra sig fig there. Okay. So that is actually the delta H0. Sorry, the delta U0. And now we need to figure out what the delta H0 is. Okay, so the next thing we have to find is what is the delta H per mole? And so this is a reaction where we have a change in the moles of gas. So take a look at this. I don't know if any of you have had a chance to balance it. Did anybody balance this equation with 1 mole of ethane? Because the delta H or the delta U per mole is really referring to per mole of ethane that reacts. That's what it means when you say a delta H for combustion of ethane per mole. We're talking about moles of ethane. So did anybody balance this, or could you do it now? Use with fractional. You're going to have a fraction here somewhere. So 6 H's, 3 waters, 2 carbons here, put a 2 there. So here I have 4 O's and 3 O's, so that's 7 O's. So it'll have to be 7 halves O2. Okay. So now, what is the delta N for this reaction? So you have to add up the moles of gas on the right side of final minus initial, right? So it's really going to be the moles of gas in the products minus the reactants. So on the, so it's be 2, because you have 2 here, water is a liquid, minus 7/2 minus 1, because ethane is also a liquid. So 2 minus 7/2 minus 1 is minus 5/2, or minus 2.5. So negative 2.5. This is the change in moles. Would every reaction of every amount of ethane have the same number of change in moles? I guess what I'm getting at here is it's really the change in moles for a reaction in which 1 mole of ethane reacts. This is actually the change in moles per mole of ethane. So if we're trying to relate the delta H, the per mole delta H, to the per mole delta U, we would use negative 2.5. B plus RT delta N. Look at this equation here, right? This is negative 2.5. But if I was going to try to relate the total delta H to the total delta U, it wouldn't be minus 2.5, would it? How would it be different? Yeah. So there's a few little details to think about in a problem like this. So if we're trying to find the delta H0 per mole from the delta U0, we would use negative 2.5 here. And look at the units here. This is kilojoules per mole, kilojoules per mole. R is, we would put it in kilojoules per mole Kelvin. So this delta N here is actually got units of moles per mole. Otherwise, the units don't even work out right. Do you see that? Of course, this is multiplied by the temperature in Kelvin. So Kelvins would cancel. So this is negative 2.5 is the change in moles of ethane, change in moles of gas per mole of ethane. But if we were trying to start with the delta U total, that was the negative 67. No, that was the, yeah, negative 67.31. That was just kilojoules. Then what would I use for my delta N here? Because look, then it would have kilojoules per mole Kelvin as my units of R, Kelvin. And then here, this would have to be moles. So this wouldn't be moles per mole anymore. It would be the total moles. So how many moles of gas really change? When you're talking about the total amount, you have to remember that you have 0.04355 moles of ethane. And you would multiply that number by minus 2.5, because this is the change in moles per mole of ethane. So you'd have to, do you see that? That you have to take the total moles of ethane that you have and multiply it by the change in moles per mole of ethane. So this really has units of moles per mole, and then moles cancel and you'll get moles. So you'd have to multiply by negative 2.5. And when you do that, you get negative 0.1088. So if you're running the reaction with 2.5 moles of ethane, the change in moles of gas is not minus 2.5, it's minus 0.1088, because you're actually using way less than 1 mole of ethane. So let me go over the 2 different approaches to this problem then. The first approach is exactly what we were doing here. The per mole one. Let's take that down here. So we have delta H0 is delta U0. These are all per mole plus RT delta N, where that is negative 2.5. So the delta U0 was negative 67.31 kilojoules per mole. Sorry, wait. Negative 154. Let's call it 1548 kilojoules per mole. And then do my calculation here. Plus 8.314 times 10 to the negative 3 kilojoules per mole Kelvin. That's the R. 298 Kelvin times negative 2.5. Moles per mole. Moles of gas per mole of ethane. And then moles cancels, Kelvin cancels. So this is negative 1548. And that term there is minus 6.19. Let's check that. 8.314 times 10 to the negative 3 times 298 times 2.5. Yeah, negative. So it's actually not a huge correction. Okay. So 1548 minus 6.19. Sorry. Okay, so you can see it's a relatively small correction there. So this is the delta H0. So let me go over what I did again. We took the calorimetry constant, multiplied it by the change in temperature. That gave us the delta U, the total delta U. But we divided by the number of moles because we wanted to find the delta U per mole. So this is the delta U0 here after we divided. Then we looked at this reaction. We saw that for every 1 mole of ethane that reacts, and this corresponds to 1 mole, so that's what we want, we get a negative 2.5 is the change in moles of gas. That's our delta N in this equation. We put that in. So the per mole method we finished with. We take our delta H0 and calculate it from the delta U0, and we put in that negative 2.5 for the delta N. We use R in units of kilojoules per mole Kelvin, and we get this number here. But the other way to do this problem, and you should know how to do both of them. I mean, it's the same thing really, but you have to know how to handle it. Is to instead of using the molar delta U and getting the molar delta H0, okay? What if instead you use the total? You start with the 67.31 kilojoules. Okay. Well, delta U, sorry, delta, I'm sorry. It's the same overall equation, but now we're using the quantity before we dealt with the, dividing by the number of moles. So in that case here, instead of using the negative 2.5, we have to use negative 2.5 multiplied by the number of moles, which, if you remember, was 0.04350. And that's how we got this number, negative 0.1088 moles. So now, to get the delta H, you just add these numbers up. So that's what this equals, 0.2696. So, you know, you get negative 67.59. So now, if you want to find the molar amount, you would just divide that by the number of moles. I'm having a problem again here. Why does this only happen with this class? Maybe it's all the math. Tablet can't stand it or something. I don't know. Okay. So this is and so now if we want to find the molar delta H, we just divide it by the number of moles. And guess what? We get negative 1554 kilojoules per mole, which hopefully is exactly the same as what we got before. But you see how you had to change the number of moles there. So that's a little subtlety of this type of problem. Okay. There are other subtleties in this type of problem. There are other things that I have not, something I haven't mentioned. Okay. So we use this equation here. Delta H is delta U plus RT delta N. And we assumed that the temperature is constant. So let me ask you something. Is the temperature really constant in a combustion reaction? You know, you burn this thing in pure oxygen, it generates a lot of heat. The temperature changes. So how is it that I can use an equation where I assume that the temperature is constant? Okay. And this is one of the lovely mysteries of physical chemistry that I'm going to explain right now. Okay, so here it is. The temperature is not constant. It changes for a while. Remember, you have this bomb inside this water bath, right? Here's the water bath. And the thermometer's out here. And you start at a certain temperature, and then the temperature goes up, and you measure that in the thermometer inside the surroundings. But what's happening to the system is its heat is leaving. It's going into the surroundings over here in the bath and is recorded as an increase in temperature. But at the beginning of the reaction, it's at 25 degrees C. So then the reaction happens, the temperature climbs, and then the heat gets transferred out. And then at the end, the temperature inside the what we call the bomb, the sample compartment here, right in here, is back to 25. So that's really all that the internal energy cares about, is that the temperature went back to what it was at the beginning. Okay, so there is a change in temperature, but by the end of the reaction, temperature changes back, the temperature is back to what it was before. There's no overall change in temperature. The temperature doesn't lead to a change in the internal energy because it goes back to where it was before. And so we don't care, and neither does delta U, what happened to the temperature in between. You know, all we care about is that the temperature at the beginning is the same as the temperature at the end. And the reason why we don't care what happened in between is because internal energy is a state function. And it only depends on the current conditions. And so that's one of the lovely mysteries of physical chemistry, that we could say, run the reaction at a constant temperature. But of course, you have reactions are exothermic, they're endothermic, the temperature changes, but then they're over and the temperature goes back to what they were before. And that's what we're talking about. That's the number that we're giving, is the delta U for when, you know, everything goes back to the way it was and the reaction happened and the heat went somewhere and we accounted for that. But we don't have to worry about the change in temperature because the internal energy is a state function. And that's sort of the beauty of the whole thing, or one of them anyway. Okay, so we can say constant temperature. All right. So I'm just going to start this other part, this other problem. I don't know how far I'll get, we'll see. Okay, so here's the other problem. And I just want to go over again what equations we have. We have delta H is delta U plus RT delta N. This is you use this when the moles of gas changes, but the temperature is constant, or at least it's the same at the beginning and the end. Then we have delta H is delta U plus NR delta T. And you use this for when the moles of gas is constant, but the temperature changes. And then we have this one, and this is the one we're going to use for this problem. Okay, and this is very good to use when you have a phase transition, where there is a large change in volume because gas is produced. Meaning, you know, from liquid or solid, or what else would it be produced from if it's a phase transition? It's either liquid or solid. Okay, so here's the problem. It says, what is the delta H for vaporizing? So we're talking about a vaporization. 100 grams of liquid water at the boiling point, 100 degrees C. Okay, and I give you that the heat of vaporization, this is the molar heat of vaporization. It's per mole quantity. And it is 40.65 kilojoules per mole. Okay. So first it asks, what is delta U for this process? So what we want to do is, well, you're given the delta H for 1 mole, right? You're given the delta H0, okay? So what you need to do is to find the number of moles. That will give you the total delta H for vaporizing this much. That's not 1 mole, right? So it's kind of like the other problem that way. Find the number of moles. The delta H would be the number of moles times that heat of vaporization. Okay, so you'll get the delta H without the little zero there. And now you can use that. So we had that delta H is delta U plus P delta V. So that means that delta U is delta H minus P delta V. Okay. And what is delta V? So delta V is the volume of the gas that's produced minus the volume of the liquid. Okay. And you should ask yourself when you do this, is this negligible? So calculate that volume of the liquid, right? Because you have 100 grams, so you know what's the volume of that going to be. It's pretty easy to calculate. Water density, assume it's
100 milliliters.
100 milliliters. That's only 0.1 liters, right? So when you calculate the volume of the gas, right, because this delta V is V gas minus V liquid, okay? When you calculate that, you'll see that this will actually end up being negligible, okay? So, so calculate that volume. Then you could find the P times V gas minus basically something that's negligible. So it's really just PV gas, okay? And you can combine that with the delta H to get what the delta U is. But there's still a couple of different ways to do this. I would like you to start working on this and see if you could come in next time with this problem done. And then I'll show you some other sort of ways of looking at it as well. Because another way to do it, so if this is P delta V, and this liquid is negligible, that really is just PV, right? And PV is nRT. So you can actually find delta U by taking delta H minus nRT. And then when you do the per mole thing, because I think it asks you for the per mole as well. No, it doesn't, but anyway, I don't want to say too much more, so I want you to just do this problem for next time. I'm not going to collect it or anything. I just want you to do it. I'm working on a quiz. I probably won't actually have it ready until tomorrow or Friday, but I think I won't collect it for a week or something, so that should be plenty of time. It's not going to, I don't think it's going to be as long. All right, so I think I'm ready to say goodbye, unless you have any questions.
Hey, Dr. Curley, when will you post these notes, like this class?
The notes, right? I'm going to post the notes right now.
Okay, thank you very much.
The recording, I don't get it. It's really weird. Sometimes the recording, I get notified by an email when the recording is ready. Sometimes it's 10 minutes. Sometimes it's 3 hours. I really have no idea why it's one and then the other. So I can't tell you more than that.
All right.
But I'll put it up there as soon as I have a chance to.
Thank you. Appreciate it.